Hello, today I'm going to be presenting a Bayesian linear regression using JASP statistical software. So I've gone ahead and loaded my data set. For this example, I will be using the student performance data set, which has student achievement and secondary education of 2 Portuguese schools. And this is a public domain data set available on Kaggle. The research question that we're interested in is, does study time and period 1 grades predict final grades? So to get started, let's select regression and then linear regression under the Bayesian heading. So we'll drag and drop period 3 grades or final grades, also G3 in this data set, to the dependent variables box. Next, we'll go ahead and drag and drop study time and period 1 grades or G1 to the covariates box. Now we can see that JASP automatically outputs a table on the right-hand side of the screen. We'll go ahead and look at the base factor, base 10. Let's compare to the null model, and let's also look at the posterior summary. So to interpret this data set, first, to interpret our output, we have our models. So JASP automatically outputs all possible combinations of models. So we have our null model, we have both of the covariates by themselves, G1 and study time, and then we have the model with the 2 main effects in it. In the next column, we have the prior probabilities. So in this case, we are not making any assumptions prior to observing the data. So we're using a uniform prior, or it's a beta binomial 1-1 prior. And in this case, when we have one variable, our prior is 0.167, and then we have 2 variables that's going to be multiplied by 2. So this is simply just dividing by the number of variables that we have. In the next column, we have our posterior, and this is our posterior probabilities after observing the data. So we have our prior, we observed the data, the probabilities are now updated. So we can see that the first and the fourth probabilities are now much smaller, indicating that they're much less likely. Whereas the 2 in the middle, this one is still the one in the second column, the 0.81, is definitely more likely than the prior. And this one is less likely. In this column, we have our Bayes factor of the model odds, and it's the posterior divided by the sum of all of the other posteriors. So the posterior odds divided by the prior odds, and that's going to give us our Bayes factor model odds. Now, what we're really interested in here is the Bayes factor, base 10. So what's happening here is that every model is being compared to the null model because it's in the first row, and we also selected compare to null. So the null model compared to the null model is going to give us a Bayes factor of 1. Now, if we compare any of the other models to the null model, they are all extremely better at explaining the data, as indicated by how large these numbers are. And then in this column, we have our R-squared value, which is the explained variance. So now if we want to determine which model is the best model, we're going to go ahead and select compare to best model. And this is going to put the best model in the first column or the first row, and then compare subsequent models to the best model. But now we want to interpret this in a more intuitive manner. So let's flip it to Bayes factor 0-1, which is going to put our best model in the numerator. So our Bayes factors are going to be in terms of the best model. So we can interpret this second row as saying that our model with only period 1 grades is 8.522 times better at explaining the data relative to the model with study time and period 1 grades. Likewise, the model with period 1 grades is 3.021 e to the 151 times better at explaining the data relative to the model with only study time. And looking at the R-squared, we can see that while there is a 0.001 increase when including study time, it is not a sufficient or possibly not necessarily a practical difference in increasing in prediction or the explained variance of period 3 grades. So now let's go ahead and look at our coefficients, our posterior summary. We can see that our probability of inclusion exclusion is 0.5 because we're not making any prior assumptions about the data. And now we have our updated probabilities as so, and then our base factor of inclusion. And this is what's telling us which coefficients should be included in the model. How much evidence do we have supporting that these variables should be included in the model? And in this case, we can, it looks like there's extreme evidence supporting that period 1 grades should be included in the model. However, we do not have any evidence supporting that study time should be included in the model. And this also is expected because we just determined that the best model only has period 1 grades. So it comes to no surprise that the base factor of inclusion reaffirms that finding. Next, we have our means and our standard deviations for the coefficients, and these can be interpreted as they would in classical or normal frequentist statistics. So for every 1 unit increase in period 1 grades, period 3 grades increases by 0.969. And then we also have our 95% credible intervals for the distributions. And that will be all.